Hello, colleague. Welcome to the lab component training video for lab week 5. So this week we are going to teach our students lab 4, the fourth laboratory session for the lab component. The corresponding theory is from the module 5. The objectives are to use Python to check whether the given system of linear equations is diagonally dominant or not, and further to find the solution of the linear system uh, if the system is diagonally dominant. Okay, so let's get started with some theory. So Gauss Seidel method is an iterative method to solve a system of linear equations. So in the entire method, the diagonal dominance is a requirement for the system to be solved using the Gauss Seidel method. Though diagonal dominance is not the necessary condition. However, diagonal dominant is a sufficient condition for a system of linear equations to be solved using Gauss Seidel method. So first, let's explore the definition of diagonal dominance. So let's consider a system of n linear equations in n variables. The coefficients are represented as a11, a12, all up to a1n, corresponding to the variables x1, x2 to xn. So the linear combination of all the variables, considering the coefficients as a11, a12, all up to 1, a1n is equal to b1, and similarly for all the n equations. Now this system is called diagonally dominant if the condition holds that the absolute value of aii for the ith variable is greater than or equal to the summation of all the other coefficients except the diagonal. In other words, if we write the system as in the matrix form, the left matrix here being the coefficient matrix, this particular matrix is X, which is the variable matrix, and this is the right hand side matrix, which contains all the constant values. So in this case, the diagonal entries A11 should be the modulus of A11 should be at least the sum of A1 modulus of A12 plus modulus of A13 and so on up to modulus of A1n. Similar conditions should be held in all the rows. Further, let's discuss what the Gauss Seidel method is. So the Gauss Seidel method, the system of linear equations has to be written in an explicit form. So for example, the ith equation has to be written as xi corresponding to the ith variable as 1 divided by aii, that is the coefficient of the ith variable in that ith equation. And that should be equal to the right hand side, which is the constant, minus the summation of the products of the coefficient and the variable except the um, ith variable. Okay, and then we use this explicit form for all the we write down first of all the explicit forms of all the variables, and then we take an initial value uh, of the particular variables of all the variables together and use this expression, this explicit form expression, to obtain the next cases. All right. The objective one was to find out the whether a given system is linearly diagonal or not. Is diagonally dominant or not. Okay. So we are assuming that the matrix, that the linear system is given in the matrix form, and we shall be using the input to this particular objective as the coefficient matrix. So the algorithm is as follows. First of all, we use the diag function from NumPy to find all the diagonal entries of the matrix. the output would be a list. Next, we use the ABS function from NumPy to get all the absolute values, the diagonal entries, which also returns a list. And we'll name that as ABS underscore diag. Then we use the sum function from NumPy to find the sum of each row. And please note here that we will be using the argument axis is equal to 1 to denote the rows. In order to find out the sum of the columns, by the way, we must use axis is equal to 0 as an argument for the sum function from NumPy. The fourth step is to subtract the uh, summation, like as the we need to subtract the diagonal entries from the summation, and we'll be getting off diagonal as a new list containing row-wise summation of the absolute values minus the corresponding diagonal entry. Finally, we'll be checking whether the ABS underscore diag list is if all the elements in ABS underscore diag list are greater than or equal to the corresponding entries in the off underscore diag list. Okay, so here is the program. So first of all, we import NumPy as NP, and this is the initialization of the particular matrix. Next, as we had discussed, we find out the diagonal values of the particular matrix A, of the given matrix A, and using the ABS function from NumPy, we find out the ABS diag, which is the absolute values of the diagonal entries. Next, we find the row-wise sum of the non-diagonal entries. So for that, first of all, we find out the row underscore sum, which is the list of the row-wise summation of the entries. For that, we already use np.absa, which is an input, which actually takes the absolute value of all the entries of the 3x3 matrix we have taken in the example over here. Please mention axis is equal to 1, which is required for taking the summation over the rows. Okay, the next command over here is off diag is equal to row sum minus ABS diag, which means that we'll be taking the summation of the row wise entries, and from that we'll be subtracting the absolute value of the diagonal entry for the corresponding row. Further, we'll be using this dot all function in order to go for a element wise comparison. So the condition here that has to be satisfied is ABS diag is greater than off underscore diag, which means that all of the entries of the ABS underscore diag must be at least or must be greater than the corresponding entries in off underscore diag. If there is even one entry which does not follow this condition, the bracketed term over here would be false, and we'll move to the else condition. Okay, so if we run this program, we shall get that the given matrix over here is diagonally dominant. Great. The objective 2 of this particular lab exercise is to find an algorithm to solve a linear system of equations in the diagonal dominant form using Gauss Seidel method. So for here we have introduced a new function, syntax called the lambda function, which is inbuilt in Python. We do not need any kind of library or packages to be imported. So we use the lambda function to define the variables, we define an initial guess, and we name that initial guess as the current approximation. And then we also specify the number of iterations. So in each step of the iteration, we use the current approximations to define new approximations, and we save the new approximations as new variables. And then we update the current approximations using the new values from the previous step. For in it should be 4.1 from the previous step. And then we print out the current approximations. So after all the iterations are done, we print the final results. It's pretty simple. Now there is an important description about the lambda function that we must tell our students. So the command f1 is equal to lambda xyz 17 minus y plus 2 star z by 20 is a one-liner method of defining a function. So in the previous lab exercises, we had seen that we use the keyword def, and then we give a space, then we name the function, and then inside the bracket, we mention all the arguments of that particular function. Outside the bracket, we press a colon, go to the next line, give an indentation, and start defining the function. And finally, we use the return function to specify what the output should be. However, here it is a much simpler method of defining a function. However, this function does not work very well for if it becomes complicated if the function itself has a complicated computation to carry on. Here we wish to take the value of x, y, z, and maybe calculate the expression 17 minus y plus 2z all over 20. So we use a lambda function, which is a simpler way of defining a function. So the syntax is as follows. First, we specify the function name, and then we give an equals sign. We use the keyword lambda, and immediately after that, we mention what the variables we are going to use. In our case over here, the variables are variable 1, variable 2, variable 3, which means x, y, and z. And finally, we give a colon, and after the colon, we define the function descriptor, which is the expression that has to be computed. So the function descriptor is the return counterpart of the def method of defining a function. Please note here that the function name is f1 and the function arguments are x, y, and z, right? So format of calling a function is we just write f1 and in the bracket we mention the values of x, y, and z, and the output shall be the expression that is being given in the function. Okay, now having said that, in order to understand the algorithm in action, we need an example. So let's use an example. So let's address a question saying that, okay, use Gauss Seidel method to solve the following system of linear equations using 5 iterations. 20x plus y minus twice z is equal to 17. 3x plus 20y minus z is equal to negative 18. 2x minus 3y plus 20z is equal to 25. So here we observe that the system is diagonally dominant. Why? Because the absolute value of the coefficient of x in the first equation is modulus of 20, and 20 is greater than the modulus of 1 plus the modulus of negative 2, that is equal to 1 plus 2 is 3. So 20 is greater than equal to 3. In the second equation, the coefficient of x is 3, the coefficient of y is 20, the coefficient of z is negative 1. And the second equation, we are interested in harvesting the variable y. So we look at the absolute value of the coefficient of y, that is equal to modulus of 20, which is equal to 20 on the left hand side. And on the right hand side, we have the modulus of the coefficient of x, that is modulus of 3, plus modulus of the coefficient of z, that is equal to modulus of negative 1, that is equal to 1. So we have 20 greater than equal to 3 plus 1, which is equal to 4. And that's true. Finally, the coefficient of z In the last equation is 20. The coefficient of x is 2. The coefficient of y is -3. So the modulus of 20 has to be greater than modulus of 2 plus modulus of -3, which is true because 20 is greater than or equal to 5. Hence, the system is diagonally dominant. Once we show that the system is diagonally dominant, this is a sufficient condition for the system to be solved by the Gauss Seidel method. Then we define on our notebooks using pen and paper that small x is going to be equal to 17 minus y plus twice z all divided by 20, and y should be equal to -18 minus 3x plus z entirely divided by 20, and z is equal to 25 minus 2x plus 3y whole divided by 20. Now let's use our algorithm to solve this particular equation, system of equations. So the first step was to use lambda to define the variables. So we use f1, f2, and f3, right? f1 for the first equation, f2 for the next equation, f3 for the last equation. And by the value of f1, we mean that we are going to find out the value of x from by using the function f2. We are going to use we are going to find out the value of y, and by using the function f3, we are going to find out the value of z. So f1 is equal to lambda xyz colon the first equation over here, 17 minus x plus 2z by 20, right? Multiplication is given by star and division is given by slash. And we put a bracket here because this entire thing is in the numerator and 20 is in the denominator. Similarly, we define what f2 is and what f3 is. Then we define what the initial guess is and the number of iterations. The initial guess would be 0, 0, 0. You can start with any other initial guess. So there is an alternate method of making the initialization using a single command. We can just write x0, y0, z0 is equal to 0, 0, 0. So maybe while solving a second problem to the student, you can ask them to execute a command like this. And also the maximum number of iterations is 5, which is given in the question. Now let's orchestrate the iterations. Let's implement the Gauss Seidel method. So for I in range max iter, the value of max iter is 5, which means that this particular loop is going to run for 5 times. If the value of max iter is different from 5, this loop would execute that many times. So first we find the new approximations. So new approximations, the calling the function is same as we had discussed a little while back while describing the lambda function. So x1 is equal to f1 of x0, y0, z0, and y1 is equal to f2 of, pardon me, this should be x0, y0, and everything should be 0, right? Pardon me. Yes, so what we do is that we define the new approximations as x1 is equal to f1 of x0, y0, z0, y1 as f2 of x0, y0, z0, and z1 as f3 of x0, y0, z0. And once we get these values, we update the approximations to the variables to the current approximation. X0, Y0, Z0 are the current approximations, right? We update those values and then we print them. Now, while printing, we have used a different way of printing in the sense that we want to see what happens iteration wise. So, iteration I plus 1, since I starts from 0, we need to do I plus 1 because iteration 0 does not make sense. Iteration 1, the first iteration. So we print x is equal to x0, y is equal to y0 and z is equal to z0. Right? We use the round function uh, to round off the output to 5 digit, to 5 decimal digits. After the decimal, there will be 5 digits. And once this loop runs for the max item number of terms, we print the final result. And that's the final result. So what is the result? Here, after the iteration 1, the value of x is this, y is this, and the value of z is 1.25. After the second iteration, the values have changed. After the third iteration, the values have changed further. After the fourth iteration, the values have changed. Of course, they are a little different. After the fifth iteration, most of the values are converging. And since we just had to go to 5 iterations, that's the final answer. Okay, so hence we have just completed understanding the lab week 5 uh, matter. Thank you so much.